Okay, welcome to Physical Science Module 16. Again, if you have any questions or concerns, email me at Mr. C at mrc@mrcscience.com. Okay, I'm going to start this one with a question that will stump many of your parents if you ask them it. What is the closest star to the Earth? Many people will say Alpha Centauri. They'd be wrong. It's the Sun. Today we're going to talk about, the Sun. Actually, we're going to talk about the solar system, the universe, all kinds of fun things like that. Okay, our Sun is very interesting. It is set up pretty perfectly for life. Our Sun is a special, kind of rare sun. One of the reasons it's rare is it's all by itself. There are a lot of stars out there. In fact, the majority of stars out there have one or more stars as companions. These are called multiple star systems or binary star systems. If you liked Star Wars, Tatooine in the skyline was a binary solar system. They had two suns. Sounds kind of cool. It'd be kind of neat to see two suns, but it can cause some problems. Having more than one star can cause not only intense changes in radiation, depending on if the stars are similar to each other. So as you draw closer to the larger one or the hotter one, it gets hotter. As you draw further away and get closer to the cooler one, it gets cooler. That can cause issues with life. Gravitational forces between them can cause lots of issues as well. It's very difficult to imagine life in a binary star system or a multiple star system. Our Sun is special because of its mass. The Sun, from what we look at, is huge. Sun's diameter is roughly 865,000 miles across. So if you drew a line, here's our Sun. If you draw a line from one end to the other, that line would be approximately 865,000 miles. The reason why that's an approximation is the Sun actually changes size slightly. It expands and contracts slightly. Diameter of the Sun is more than 100 times that of the Earth. So if you took the Earth about 1/100th of a time, I don't think I can draw a circle that small, so it's probably smaller than that. But you could fit 100 Earths from one end to the other, or over 1,000,000 planets within the Sun itself. So the Sun is extremely massive, but on the grand scheme of things, the Sun is not one of the more massive stars out there. Mass increases gravity, so the greater the mass, the closer, the more the gravitational pull, either the faster your orbit has to be, or you have to be further out or closer in. So lots of things with the gravity of the Sun that can cause problems. A combination of the mass and the size make it a perfect Sun for us. So, what is the Sun made of? It's primarily hydrogen, with some helium. The reason some helium is in there is because the Sun goes through nuclear fission and combines hydrogen to make helium. Go ahead and you should have your books. Go ahead and turn to page 3. We're going to go to 399 first and show nuclear fission. So on page 399, figure 16.1, you see a H1 hydrogen proton. Basically, the Sun is huge, it's massive, lots of hydrogen in there. In fact, it gets so hot that the energy causes the electrons to leave the orbit of the hydrogen atom. So the hydrogen atom is all by its lonesome with just a single little proton there. Hydrogen, we learned earlier on, has different isotopes. Isotopes are just basically differences in the atomic nucleus. So hydrogen always has one proton, but sometimes hydrogen has a neutron. That's called H2 up here, H1, or basically you squash hydrogens together under intense heat and pressure, and you get an atom with 2 protons, and in this case 1 neutron. Atom with 2 protons is helium, so boom, it goes like that. What happens when that happens is you lose a little bit of mass, not a lot, but just a little bit. But when you lose that mass, guess where it goes? It becomes energy. And using a formula that's very familiar to a lot of people, E equals mc squared. What that stands for is energy equals mass. So this mass is being converted to energy. So energy from the mass times c is the speed of light squared. So c is the speed of light squared. It's a huge number. So you get a lot of energy from a little bit of mass. That's why nuclear explosions are so large. The mass is relatively small, but the energy released is humongous. Let's back up just a little bit and let's look at figure 16.1, the sun itself. So the sun has layers, much like an ogre. No, that movie's probably too old now. People probably don't get that reference, but here's our sun. It has layers. Now we can really only see the outside layer called the photosphere. Under that photosphere is a layer. A lot of this is from math and other observations. Under that photosphere is an area called the convection zone. It's called convection zone because there's a lot of movement. Things go in, things go out, things go out, things go in. So underneath that is a very large area called the radiative zone. We'll talk about that more. And then inside is the core. The core is where nuclear fusion occurs, although a little bit can occur in the radiative zone. Okay, so let's talk a little bit what happens then. So the core itself, under extreme pressure and heat, the temperature of the core is about 27 million degrees Fahrenheit. Again, how did they figure this out? Did they send thermometers in there? No, it's a lot of math. Million degrees Fahrenheit. So this is where most of this fusion happens. Now when that happens, the energy lost is sent out in what's called photons. Now photons sound familiar because you probably heard of them before. They're light. In fact, we talked about photons actually, energy packets. So those photons, mostly light, head into the radiative zone. So now they pass through the radiative zone. It's not enough pressure here to cause a lot of fusion. A little bit can happen, and then takes a long time for that photon to go through the radiative zone. Then it gets to the convective zone. The convection zone, gases go up, gases go down. The photon is released and into the photosphere, the outside edge. That's the part that we actually see, where it cools down a little bit. People often say, well, the sun is a big burning ball. Well, actually it's not burning at all because there's no oxygen to combine up there to cause the burn. It's actually fusing. It's nuclear fusion causing it, all that heat. And as you heat something up high enough, it releases light, or photons. Those photons then travel away from the sun and off to our planet, keep us nice and warm. You read a little bit about solar flares. We're not going to get into that. So this up here is called nuclear fusion, where we fuse 2 or more atoms to make a larger atom and release energy. So what we do in our nuclear power plants is something called fission. Nuclear fission is the breaking of an atom into 2 smaller nuclei and releasing energy that way as well, using the same E equals mc squared mass. Mass is given off or converted to energy here as well. Turn to page 402 and you'll see you've got uranium-235. Oh, I put my numbers on my hydrogen in the wrong place. You got uranium-235, which we use in our nuclear reactors. Although I don't know if plutonium is more of a weapons grade, so I think they primarily use uranium at this point. but I don't know for sure. It's been a while since I've looked into that stuff. So what they do is they take a neutron and they slam it into uranium-235. What happens is that causes it to break into two smaller protons, or two smaller nucleuses of protons and neutrons, and it releases more neutrons, as well as some mass, which is converted to energy. So what's interesting about that is uranium-235 is actually mined. You can find it in the ground, but it doesn't cause nuclear fission all by itself. What you have to do is you have to get together something called critical mass. Critical mass is the amount of isotope necessary to cause a chain reaction, or to sustain a chain reaction. So what that chain reaction means is you got this neutron goes into the 235, breaks it, releases 3 more neutrons. If those neutrons can find more uranium-235, they can cause the same reaction, can release 3 more neutrons, and so on, and you get what's called a chain reaction. So each of these breaks generates some energy in the form of heat and photons. So you can keep it going. So in a bomb, U-235 can be used in a bomb. It was used in a bomb that dropped on Hiroshima. Plutonium's better for that, but a bomb has a large, much greater than critical mass. So critical mass is kind of a fine line. If you can stay near that critical mass or just above it, you can control this chain reaction, and you don't get an explosion. You get the generation of heat, and use that heat to boil water, turn turbines, and generate electricity. So a nuclear power plant itself, they control how much is there, and it can a nuclear power plant itself can never explode. There isn't enough mass in one place to cause a nuclear explosion, chain reaction. What it can do, and what's happened in places like Chernobyl, is it can go into meltdown. Meltdown is caused when it runs ahead, it's not cooled enough, they don't control the reaction, and thus it generates a lot of heat at one time, more heat than it can handle, and it tends to melt the containment area around it, and thus the reaction is no longer controlled. Meltdown can cause the release of radioactive isotopes into the air, into the soil, into the water, which can cause problems. Was it this week or last week? No, last week or last time you learned about half-life. So radioactive material has a very high half-life. So it takes a long time for those to break down to where they're not dangerous anymore. They're not giving off radiation, which can be dangerous to life. Okay. They'll talk a little bit more about that, but let's go into classifying. Let's get back to our sun. Sun uses fusion, not fission, and sun creates helium. Let's talk. Go ahead and turn your books to page 405. The sun has a certain temperature. The temperature of the sun is approximately, on the photosphere, is approximately 10,000 degrees Fahrenheit. What's interesting is they use Fahrenheit when every place else in science we use Celsius, but that's right. Okay, on page 405 is a table. I believe you do not have to memorize this table, but it's useful because as they measure the temperature, they give it a spectral letter. So our sun is about 10,000 degrees Fahrenheit. So that means it is a spectral letter of G, I believe. Yes, we are a G star. Almost up into the next. So a spectral letter of G is its classification for its temperature. Now they can classify, first of all, how did they tell the temperature of our sun or the temperature of other stars? They used a thing called spectroscopy. You'll get more into spectroscopy if you get into chemistry more heavily, or some advanced physics and astrophysics, things like that. But they can use spectroscopy to approximate the temperature of the star. So you can see on this table in here, they got less than 5,500 degrees all the way up to over 37,000 degrees Fahrenheit. So, and based on that, they give the star a spectral letter. I do not know if it goes into what those letters mean. I don't know myself. I'm guessing they're probably Latin or Greek, but you never know. Okay. So they classify stars by temp. They also classify stars by brightness. Brightness seems pretty obvious, but there are two types of brightnesses we deal with. Now, what we see in the night sky is it's apparent. It's apparent magnitude. This is the brightness of the star when we see it. So if you're standing here, you're looking off in a far distance at a star that is millions, if not billions of light years away, or at least hundreds or thousands of light years away. And it appears to be relatively dim. Now, if you were standing right next to the sun, which would be much bigger than that, first of all, you would burst into flames and evaporate and all kinds of fun stuff like that. But if you could stand right next to it, it would be much more bright. Take our sun, for instance. We're close enough that you can't stare at the sun. It will damage your eyes. So the intensity is great. But if you go out to, say, Pluto, you could look at the sun all you want. It appears to be a very bright star in the sky. So the apparent magnitude, when you get close enough to see the sun or the star right next to it, that's called absolute magnitude. Now in classification, they care about absolute magnitude. How bright is that star? On page 401, you got what's called a Hertzsprung-Russell diagram. Guess who invented that diagram? Two guys named Hertzsprung and Russell. So, okay, and it's also at times called an HR diagram. Now, you do not have to memorize this diagram. It will be given to you to use on the test, and you can use this on the study guide as well. You'll notice across the top, the diagram has two different parts. So across the top are those letters, O, B, A, F, G, K, and M. And across the side are -10, -5, 0, 5, I'm going to extend it, 10, and 15. Okay. So across the top is our spectral letter, which stands for temp. And we go from coolest to hottest going this way. So we got our coolest temps here, we got our hottest temps here. Okay, on the other side is its absolute magnitude or brightness. Okay. We go from our dimmest, which really isn't that dim, although it can be, all the way up to our brightest. Okay, our sun was spectral letter G, so if we draw a line down here for G, and the absolute magnitude of our star, I believe, is around 5 in brightness. So our sun falls right here on the diagram. Okay, so you'll notice that this diagram shows some interesting things. First of all, wandering through the middle is a bunch of stars. These are called main sequence stars. our sun is a main sequence star. They're similar. The suns can get very bright and very hot, and very cool, very dim. You'll notice that the temp and the brightness seem to be related to each other in these stars. So as they get brighter, they get hotter. As they get hotter, they get brighter, and vice versa. Okay. There are 3 other types of classifications here. We got here our red giants. We got our supergiants. And then we got our white dwarfs. Our white dwarfs, okay. So let's talk about the different types here. So you'll notice also on the diagram that they got blue to red. This is just kind of a color. Blue, the blue, red, the red spectrum, shorter wavelengths, longer wavelengths. The stars all appear pretty much white. So, but this is just basically using spectroscopy again and where they fall along that. Okay. We talked about main sequence. Our main sequence generally convert hydrogen to helium. But let's talk about red giants. This isn't the case for red giants. Red giants' core is mostly made of helium. So start out with helium. And what they do is they combine a bunch of them together to give us carbon. So they convert helium into carbon. It's a little bit different, same type of fusion. Significantly hotter than our sun. So if you notice, or no, not significantly hotter. They're not significantly hotter. In fact, they tend to be a little cooler. So this gives off a different type of energy also. Plus, they tend to be much more massive. If a standard red giant was in our solar system, the star would reach out to about the orbit of Saturn. So we would be inside the star. So good thing we're not a red giant. We're a main sequence star. Okay. If you look at the supergiants, guess what? They're even bigger. Supergiants are the largest stars in the universe. Red giants would just engulf the inner planets. Supergiants would be the ones that would get out to Saturn. So very large, but also extremely rare. Have a large band, but they all tend to be very bright, mainly because of their size. White dwarfs are quite small. An average white dwarf is about the size of the Earth. So they're relatively small, and they also tend to be relatively dim. So they believe that we can't see all the white dwarfs in the sky that are around us because they don't give off enough light. Interesting thing about the white dwarfs, though, is they're very hot. The reason they're very hot is they have a lot of mass. White dwarf is all compressed down. Example of a white dwarf would be a neutron star. A neutron star is compressed so far down that it is just neutrons. No electrons, no protons, no electrons, no protons, just strictly neutrons. So very tightly packed. A teaspoon of the stuff on Earth would weigh several tons. So incredibly dense stars, not really gaseous. You could fly into the edge of a red giant, or you could fly into the convection zone on our sun and possibly pass through it, much like passing through a very dense gas or a liquid. But white dwarfs are very dense. You wouldn't be able to do that. Okay, so know this diagram. Don't have to memorize it, but know cool to hot, dim to bright, that ours is a main sequence. So we got your red giants, your supergiants, and your white dwarfs. Okay. Now let's talk about another type of star. So this uses brightness and heat. There are stars that don't have a standard brightness. These are called variable stars. Variable stars, they vary. So generally, their brightness varies. Two types of variable stars: pulsating and novas. Pulsating variables, as it says, they pulse, so they get brighter, dimmer, brighter, dimmer, brighter, dimmer, brighter, dimmer. Novas just change. So novas are probably the most spectacular. They're called novas because nova means new, and originally they thought they were new stars that were appearing in the sky. But really what they are is they're exploding stars. So the star will explode, it will give off some of its mass. Now it doesn't mean necessarily the star is destroyed. The star will eject mass. And when it does that, its brightness increases. So some novas will eject mass and then go down, and then later on eject more mass, go down, later on eject more mass. They don't eject a ton of their mass, so they can do this for quite a while. But it causes a temporary surge in brightness. Some novas, called supernovas, are where the sun actually explodes. This is a one-time occurrence. So once they explode, they generally leave behind a cloud of gas called a nebula. If you turn to page 410, there is a picture of the Crab Nebula. In 1054 AD, early astronomers recorded observing a flash of light in the sky. If we look at the same position today, with our telescope, especially Hubble, we can see the Crab Nebula, and there's a picture of it. So there is a sun that exploded. Now, we saw it in 1054 AD, but it exploded earlier than that because it takes light a certain amount of time to get here. So whenever you're looking at the stars, you're actually looking into the past, where they were. Okay, so that's novas. Pulsating variables. Pulsating variables do not eject mass. They change size, often through expansion and compression, in regular periods. Well-studied classes are called Cepheid. Cepheid variables. Okay. The reason they're so well studied is they're very constant. Excuse me. Okay. They are used by astronomers to measure long distances. So we're going to talk about that a little bit more in just a second. But another type of variable can often be a binary star, or what's called an eclipsing binary star, where two stars are in orbit around each other, and at times in our field of view they cross in front of each other, in which case the one is blotted out by the other and it will appear slightly dimmer. So this is also a type of variable star that isn't a true variable star. Okay, let's talk about how we tell how far away the stars are. Oops. Control delete. Go back to the top. Okay, how we tell how close the stars are, there are two methods. The first method can be used to up to several hundred light years, or hundreds of light years away. And this method is called parallax. The parallax method uses, let's say there's a nice picture of it on page 411. I'll kind of try to approximate that. But basically what happens is our Earth goes around the sun. And there's a star out here. Hey, look at that. When we look at the star, we can find an apparent angle based on another point or a direction. This angle, theta, we'll call it theta 1. Okay, we get to the other side of our sun and we look at it later. Now this angle is going the other direction, theta 2. If we put theta 1 in here, we can see that theta delta, change in theta. So you can tell by this change in theta and how far this distance is, you can use that in a little trigonometry to calculate the distance to the star. If we were in school, we'd do a little experiment using parallax to calculate the distance to relatively nearby objects, to show you how you can use that. But it uses some uses a little bit of trigonometry. This method is good unless the sun gets or the star gets very, very far away, to the point where, if we're looking at it, the point where it almost appears to never change. So there's a point where our measuring equipment can't tell that it's changed. It's so far away, it's effectively a straight line for us, and there's no effective change in parallax. So that's good up to, in relatively nearby stars, I want to say it's a distance of a few hundred light years or so. Okay, so that's how we can tell that stars are at least a few hundred light years away. So how do we know that some of the stars are billions of light years away? That we know through a method called apparent magnitude method. So now remember, apparent magnitude is the magnitude that appears in the sky when we observe it, not that right next door. Now how we can use this is we get to these Cepheid variables. Remember the Cepheid variables we just talked about? Well, it turns out that Cepheid variables, their magnitude, I can't spell, is related to their period, or how often they vary. So, in fact, we found that it can be very predictable. So, period. So if we know its magnitude is related to its period, and we can make a chart of period versus magnitude, then we can figure out its absolute magnitude, what the brightness of the star is if we're right next to it, and using its apparent magnitude we can figure out, well, how much does the light disperse as it heads out, and we can get to our distance. You ever wonder why a star is brighter the further away you get away, or why light is dimmer the further away you get away? Well, what happens is light has so much energy, and that energy radiates out in whatever directions it's allowed to go. Now, if you're really close, you can see a lot of it. If you're further away, you can see less light. Some of the light doesn't go directly towards you. And the further you're away, the more it spreads out, and this spreading causes a dimness. So, okay, so we can use apparent magnitude and the period of a Cepheid variable to say how far away this is. And this works for very long distances. So let's talk about light itself. So how can we figure out the distance? Well, when we talk about cells, we use a distance called the light, or cells. So if we talk about stars, we use a distance called light year. And really all that is the distance that light travels in a year. Well, we know as far as miles, that's about 386,000 miles per second is how fast it goes. So then you figure out how many seconds in a minute, how many minutes in an hour, how many hours in a day, how many days in a year. And from that you can get a huge thing. Your book comes up with about 6 trillion miles. That's 6. Thousands, millions, billions, trillions. So that many miles. Huge number. So that's how fast it takes light 1 year to get there. So if you look at a star that is 15 light years away, you're seeing that star as it was 15 years ago. So the light that's traveling. If you look for a star that's 15 billion light years away, you're seeing one that's 15 billion years in the past. So, and we'll talk about how we how we reconcile this with a universe that maybe, according to the Bible, is only about 7 to 10,000 years. So, but we'll get to that here in the end. Okay, galaxies. Let's talk about galaxies. So we got our solar system. Our solar system is a galaxy. A galaxy is called the Milky Way. Our galaxy is a spiral galaxy. Turn to page 413. We have a spiral galaxy. We have lenticular, and we have elliptical. Now they have sub ones in this if you get into astronomy that'll go on, but we are a spiral galaxy. You'll notice it has spiral arms that go around. A lenticular galaxy is like a spiral galaxy, but there are no arms. Everything is very nebulous, very spread out. And then an elliptical galaxy is just a bunch of stars all grouped together in a globular form. Okay. If it doesn't match any of these, then it's called an irregular galaxy. Okay. So we see lots of them. We live in the spiral galaxy. Kind of interesting. We live near one of the arms, the Orion arm. We don't live in it. And a couple interesting things that show that maybe we were designed to be here. If we were in the arm, the gravitational pulls of all the nearby stars would cause issues with our solar system, and life could not exist. Our orbit around the center of the galaxy. So here's the center of the Milky Way. It's got its disk around here and its arms going out. So we're on the edge of an arm. Our orbit is the same speed as the arm, so we never really get closer or further away from the arm, so we will not pass through it. Our orbit is relatively circular, so that we'd never get near this huge conglomeration of stars and black holes and stuff in the center, which would tear apart the Earth and our solar system as well. So it's almost like we're in a special little place here where life can exist, where we got enough stars in the sky, we can see the neighborhood around us, but nothing really close to interfere and cause us issues. So it's kind of a cool thing. You'll read about groups and clusters and superclusters in the universe. But let's get back to our light year here. So if we had light here, and if using Cepheid variables, we can tell that stars are at least millions of light years away, if not billions of light years away. And the Bible says that the universe was created in about 7,000 to 10,000 years ago. How can we see stars from light? This used to be a problem. People said things like, well, maybe God created the light in transit, which is kind of a goofy thing. He created history, but it really wasn't history. It could be, maybe God, at one time the speed of light was greater, and thus everything came to us, but that causes problems with physics and things like that, and the laws of the universe, and it would cause lots of trouble, and really isn't possible. Within my lifetime, and he's still around, you could read his book. There's a guy called Dr. Russell Humphreys. And I probably misspelled his name, but I'm writing so terrible you can't tell. He had an interesting postulation that we can actually confirm. As gravitational potential increases, time slows down. You'll see this in many movies and sci-fi stuff. But basically, the real simple way to state it is if more gravity, the slower the time. Less gravity, faster the time. And we can measure that. If we got our Earth here, there's our Earth. Now if we have someone with a clock on the Earth, and someone with a clock in a very high altitude plane, or say a space station, and we measure the time, if those clocks are very accurate, we measure the time, we find that time goes slightly faster out there. Now we're talking fractions upon fractions of a second, but enough that we can measure, so time goes slightly faster the higher up you are. This is a measurement. This is called time dilation within a gravitational potential. This will not be on the test, but So what's kind of interesting is in the Bible it states that God stretched out the heavens, and first everything was mass called the waters, and inside he separated the earth, the waters from the waters, it said, and created the earth. Then he stretched out the heavens. As he stretched out the heavens, all these galaxies and stars and things started popping into view. So as he stretched out the heavens, these popped into real time because their gravity went to normal. Gravity in here with this large mass was intense, a lot of gravitational potential. So as this got smaller, more and more popped into view, and as it got smaller, time started speeding up into here until finally it was completely stretched out that time was back to normal here. If that's true, it's possible that one day could have went by at the center of this mass, while billions of years could have went by for the edges of the mass. So that means, how old is the universe? Well, it could be 7,000 years. It could be billions of years plus 7,000 years. So both are true. So time went by a lot faster and a lot longer out here as God stretched out the heavens. So kind of an interesting thing. Is it proven? No, it's a theory. But what's interesting is this they can show actually happens. So it's kind of an interesting theory, and it's one of the last pegs to fall in the creationist view here. So they'll talk a little bit about Doppler effect and fun things like that in there, and the expansion of the universe. I'm going to let you read about that yourself because we're getting a little long on this anyway. So again, if you have any questions, email me at mrc@mrcscience.com. Thanks.